Last day. Okay, morning. Sorry. So I forgot to record and I already gave a spiel to everyone else. We're going to do some review today. That's the summary of what's happening. Before we start the review, does anyone have any questions from assignment number 6, which is due this evening? Is it 5B part A? Yeah, then the expectation would be to do it by hand in that case. Like it's still the same separation in ideas, like part A is by hand, part B is our commander. Any other assignment 6 questions? How many people are here? No? All right, I'm gonna move on. Slowly moving on. All right. Okay, cool. Okay, so as I mentioned, the purpose of today's lecture is just to do a bit of review for the final. So first things first, when is the final? It's next week. Okay, so this date is given in a number of different spots. So it should be in your student system. It should be in the course outline. It's also going to be on this slide. So the final exam date is Thursday, December 16th, 2021. So that's next Thursday. And it is from 9 a.m. to 12 p.m. And it will be held on CrowdMark. Okay. So that's the same as midterm. Okay, so the final exam is next Thursday from 9 to noon. It's the same for every single student, regardless of the section you're in. So it's very convenient in that sense. Everyone is writing at the same time. It's going to be held in the exact same format as the midterm was held. It's just a longer time frame. So you have 3 hours to complete the exam. If you have accommodation, I'll email you separately to sort that out. But in general, every student or the majority of students will have 3 hours to complete the exam, and it will be run via CrowdMark. The link will be sent the morning of the exam, so at about 8:50, and you will have until noon to submit everything. So all photos for every question. And then it's a 10% penalty for every minute, same as the midterm. Okay, so let's talk a bit about what you can expect on the test, okay? Okay, so this is what we've covered throughout the year. So we started off with some definitions. So we had data, variables, statistics, study types, etc. Then we did descriptive statistics. Right, so in this unit, we had things like measures of center, spread, bar chart, bar plots, histograms, box plots, etc. Unit 3 was the probability unit. Okay, so in this unit, we studied all different types of probability. So we had the fundamental, we had things like union, intersection, independence, what else did we have? Mutually exclusive, etc. Okay. Unit 4, we did discrete probability distributions. So this was the general slash, like that I said slash, general and binomial. I'm recording this, right? Good, okay. Number 5, we did continuous probability distributions. So again, here we had general and we had the normal. Okay, so this would be kind of a key topic, right? Because everything we've seen, or the majority of the techniques that we have seen, usually have a normality assumption. So it's very important that we understand what it means for something to be normal. And it's important that we understand how to work with the normal distribution. Okay, in number 6, we did sampling, distribution of sample mean. Okay, and then this included the central limit theorem, which again is a very important topic as we've used the central limit theorem on a number of different situations. Okay, and then this is where the midterm was. Actually, all right. Okay, so post midterm, we did one sample confidence interval. Then we did one sample hypothesis test. Then we did 2 sample confidence interval slash hypothesis test. Then we did chi-square hypothesis tests. So these were the goodness of fit test and the independence test. Then we did the ANOVA. And then we finished off with simple linear regression. Okay, so the midterm, or the final rather, is going to be focused on these parts here. No, do it like this. All right, so one of the questions that comes up a lot and will come up quite a bit even after today's lecture is the final exam cumulative? Yes, the final exam is cumulative, but it's weighted towards the second half of the course. So it's weighted towards everything that I've highlighted post midterm. Now, what does that mean in terms of studying? Does that mean that you can ignore the material from before the midterm? The answer to that is no. The reason that the answer is no is because a lot of the things that we studied before the midterm, we need for the final. So, for example, you have to understand what it means for something to be normally distributed. You have to understand how we can use the central limit theorem to check assumptions of the 1 and 2 sample hypothesis tests. You have to understand how to interpret a histogram or how to interpret a box plot, because those can be used to check the assumptions of our hypothesis tests. You have to understand how to compute a mean, how to compute the standard deviation. You have to understand how to interpret those values because they are used in the hypothesis tests. So again, the final exam will be weighted towards the second half of the course. So it will be focused on testing your understanding of everything from lecture set 7 through lecture set 12. But that does not mean that you can ignore the first part of the course, because if you don't understand the key topics from the first half of the course, you're not going to be able to effectively deal with the types of problems that you're going to see on the final exam. Because if you don't understand what a sample mean is, and you don't understand what the sample standard deviation is, I don't understand how you're going to be able to carry out a hypothesis test appropriately. If you don't know how to work with the normal table, you're not going to be able to do some of the hypothesis tests that we are going to look at. So it's important that you understand the material or the key topics from before the final exam. So normality, central limit theorem, descriptive statistics, and that you're able to apply those in the context of hypothesis testing and confidence interval construction. Once you have that foundation kind of set, then you would go through and practice all of the different techniques that we studied post midterm. On the course website, I have posted practice problems and a sample final exam. You'll notice that those practice problems and the sample final are again cumulative. So they will ask direct pointed questions from the first half of the course. Some of those problems you're probably not going to see on the final. So a lot of this stuff from the probability unit, so checking for independence, like the addition rules, mutually exclusivity, that sort of thing, probably not going to see that on the exam, but it's still worth reviewing just in case. And for the most part, you'll find that sample final and those practice problems focus on the second half material. So there's a lot of hypothesis tests, a lot of confidence intervals, interpreting those results, that sort of thing. And that again is the focus of the exam. Okay. in terms of format, so okay, it's going to be similar to midterm. So it'll be a mix of multiple choice and short answer. There'll just be a few more questions because it's a longer time frame. For those of you who are going to ask, so in the winter 2021 semester, there were 5 multiple choice and 8 short answer. Okay, so I don't have the exact format of the test yet. Like I still have to tweak it, but the last time I gave a final in this class, I had 5 multiple choice and 8 short answers. So it'll be something kind of in that range, but it's not going to be exactly the same. So I might have a few more multiple choice this time around, maybe a 1 or 2 less short answer, that sort of thing. So it's not an exact number, but this is how it was set up in the last iteration. So it'll be something kind of in that range. And I don't. And it was something like approximately 110 marks. That's twice that of. I think so. I can check. Yeah, the midterm was 5 multiple choice and 5 short answer. The first question, I'm not counting the very first question because Q1 isn't a question. It's just asking you for a signature. So I'm not including that. So in terms of like marks, it was approximately twice that of the midterm, but in terms of actual number of questions, it's not all that different from the midterm. There's a few extra questions. So 8 as compared to 5, for example. But hopefully it shouldn't take 3 hours to finish it. It should probably be doable in about 2 hours to 2.5 hours. And then you have lots of time to review and post your photos of the answers and whatnot. Okay, so any questions? It's not a guarantee though. I don't want to give anyone like false, but that would be the, like in writing it, the goal would be that the average student can finish it in about 2 hours to 2.5 hours. And usually with the final, my experience with CrowdMark testing is the midterm is always a little bit more rushed and students are trying to submit everything at the last minute. With the final, that doesn't tend to be as much of a problem because of that extra time frame. Any questions? No, the semester's done tomorrow, I think. Last day of class, December 8th. Tomorrow is the last day of class. So this is our last semester, our last class for this semester. And exams start on the 10th. So that would be Friday. And they run until the 18th. So 10 to, what's that, Friday to the following Saturday, I guess? Excuse me. So the Blackboard, this course on Blackboard closes on December 31st. So you'll have access to the materials until December 31st, and then it goes into the vapor. Disappears into the matrix. Exactly. Yeah, so actually, if you do need something, like if you want to, I don't know exactly how everyone's been keeping notes and whatnot, but if you're registered for Stat 252 in the future, for example, it's in your best interest to save hard copies of the things that you think you'll need for review, essentially, before the 31st of December. But if you've been keeping your own notes on your own machines, then that's not going to be an issue. Any other questions? Yeah. Yeah, same as the midterm. Yeah, it's online. It's in the final exam folder. Yeah, so if you go to the final exam folder in course content, it's the first item in that folder. Yeah, and also like on the note of open book, I just feel like it's important to put a disclaimer on that. While the idea of something being open book is typically comforting, if you don't study for the test because it's open book, you're not going to do well on the test. Like there's really, like if your strategy is to just look up for the topic as you go through it, it's probably not going to work out very well for you, because the amount of time that goes into looking up the topic and then trying to make sense of how to manipulate what is written into the context of what the question is, like you'd actually be surprised at how much time is wasted in that sense. Like the best way, yeah, exactly. Like it's the best way to prepare is to study for it like it would be any other exam. And then if you do that, what's going to happen is you're going to recognize topics faster. So if you do need to refer to something, you'll know where to look and you're going to know what you're looking for. So it can be used as an aid in that sense. But the students that try and just like get through it by referencing on the fly, like they don't tend to do very well. It's the students that prepare for the exam in the same way they would any other that tend to do well on the exam. So your choice, but that's my advice would be to treat it like any other test and study for it like any other test. So do the practice problems, do the sample final, review your assignments. Like the best way to prep is to just do problems and make sure you understand like what unit you're studying from. So that way you'll recognize the question when it pops up, like, oh, chi-square test, one sample t-test, regression problem. Because that once you have, if you can link those, it's going to be much easier to work through the problems. And if you need to reference something, you'll know what you're looking for. So that would be my advice. But you know, you can tell me to shove it, like it's your call. But that's my advice. Any other questions about the format or the contents or anything? Review is for you guys, so anything flies. All right. Okay, so let's look at some problems then. So again, I have four practice problems that were just kind of pulled from random parts of the course. We have an hour left, so hopefully we can get through most of them, but I'll post the solutions to whatever I don't get covered today for review. Okay, so most of these questions are, they're not like step by step, like do a hypothesis test, do a confidence interval. They're these questions are more so like picking away at different aspects of what we studied. So I think these are good problems for us to work on as a group, and they tend to be a little bit shorter, but they do require that you understand what unit you are in and how the test or the interval works so that you can pick apart the different aspects of those procedures. Okay, so the first problem, we have a random sample of 18 artifacts were excavated from the Tabun cave in Israel. The average thermoluminescence age of the artifacts was found to be 260,300 years, with standard deviation 47,600. Okay, so let's just think about this for a second. What are we being told? We have a random sample of 18 artifacts. We have the average thermoluminescent age, which is 260,300 years, and we have the standard deviation. Okay, so if we were to summarize this, we have n is 18. This is telling us that x bar is 260,300, and little s is 47,600. Right, so we are given a sample, and then we are given the statistics from that sample. So x bar and little s. Okay, part A of the question says or asks, what is the unit of measure how do you know if it's population versus sample? Yeah, because it tells us it says a random sample of 18 is collected, and then it says the average thermoluminescent age of these artifacts. So the question is telling you that we have the average of the 18 artifacts in the sample and the standard deviation of those 18 artifacts. So that makes it this, it makes it by definition the sample values. So that's why it's the sample mean and the sample standard deviation. Cool. Okay. All right. So part A, this is I like this question. It's not overly complicated, but it's a little tricky, I guess. What is the unit of measure for the standard deviation? All right. So does anyone have any idea what unit we attach to standard deviation? You can either answer in the context of the question or you can give a general answer if you think you know. Yeah, that's right. So Meg's got it right away. It's the years. So the standard deviation actually shares the same variable as the mean and as the data itself. So standard deviation has same units as variable and sample mean. So it would be the TL years for this question. Okay, so the answer we're looking for here is the thermoluminescent age. So the years for this, or years on its own is fine as well. So it's just years. So the standard deviation has the same units as the variable, which would have the same units as the mean or any direct value coming from the sample. Okay, so good. That's good. That's good. That's good. Okay, part B. Researchers want to test that the true mean age of the artifacts is no more than 230,300 TL years. What assumption would you stress they validate before performing the test? Okay, so let's just make a few notes here. We have one sample of information. Okay. They want to test that the true mean age of the artifacts is no more than 230,300 years. Okay. Oh, sorry, is more. I was reading that wrong. Is more than. Okay. So that means they want to do, if we were to write it out, we would have mu equals 230,000. Remember that the null is always a quality in our situations. And then the average or the alternative would be that it's greater than 230,000. So this is actually what they're interested in testing in the context of a hypothesis test, right? So we know that there are three assumptions: SRS, normality, and we can also say sigma known. Okay. So we actually know that it's a random sample because we are told in the question that we have a random sample. We don't have sigma, but that doesn't matter because even if we don't have sigma, we can just run a t-test, right? So that's not a big deal. So the thing that we don't have we don't have any information of is whether or not the population that we sampled from is normal. So if there was one assumption that we wanted to stress that has to be validated or tested, it would be the normality assumption in this case. The sigma is population standard deviation. So if there's one assumption that we wanted to stress that they test, and this is pretty much the case for most of the hypothesis tests we've seen in the course, it would be that normality assumption, okay? Okay, part C says, what are the null and alternative hypotheses for the test? So we actually already wrote this down in part B. So this would just be what's given here. All right. So in part D, it says, if the test statistic for the test described in B is equal to 2.701, what is the conclusion of this test when alpha is 0.05? Use the critical value approach. Okay, so if we were to think about this, we are being told the test statistic. So that effectively means that we are being given our step 3 value. So if we were to think about the hypothesis test, we have the value that is given on step 3, which is the test statistic. The question also gives us our significance level. So depending on how you write your hypothesis tests, this would be, for example, what's given on step number 2. So that's our significance level. We have our null and alternative hypothesis from the previous question. So what we are being asked to do here is simply work through the critical value approach. And then from the critical value approach, make the conclusion or make a decision about, or from the critical value approach, write the conclusion of the test. So basically what we're doing here is working through step 4 through step 6 of the hypothesis test. Step 1 through step 3 have already been given to us. Okay, so if we're going to do the critical value approach, we start by sketching out our T curve. Okay, here's 0. We're going to need a T value on 0.05 and 18. Or sorry, maybe it's 17. 17. So we're doing a one tail or an upper tail t-test for one sample. We have a significance level of 0.05 and we have 17 degrees of freedom because our DF for a t-test is sample size -1. All right. So now we need our t-table. Okay, so we're 0.05, 17, so that gives us 1.740. Okay, so here's the critical value for this test. Okay. And then we can see that our test statistic is inside the rejection region. So that means that we can reject H0. And then what the question is actually asking for is step 6. So the conclusion is what we want in this case. So here we would have at the 5% significance level, the data provide sufficient evidence that the mean TL age is greater than 230,000 TL years. Or I guess I don't need TL twice, years. Okay. And this is, again, actually what the question is asking for. Right. Okay, any questions? All right. Okay, question or problem 2. According to an article by A. Ehlers, the mean duration of imprisonment for East German prisoners with chronic PTSD, which we're going to call mu, is normally distributed with sigma equals 42 months. Compute the required number of East German prisoners needed to build a 90% confidence interval with margin of error 12 months for the true mean duration of imprisonment. Okay, so what is happening here? In this question, we actually want this. So we want to find N for a 90% CI if E is equal to 12. Okay, so what part A is actually asking us for is sample size. So we are trying to find the sample size required to build a 90% confidence interval when the margin of error is equal to 12. Okay, so to do this, first, recall that a confidence interval for one sample when sigma is known is X bar plus or minus Z alpha over 2 times sigma over the square root of N. Okay. So this is a confidence interval when sigma known. Okay, now remember, and then the second part is, this is our formula for the confidence interval. This is the margin of error. Right. So what we are being told here, or what we can then say is E, which is the margin of error, is equal to Z alpha over 2 times sigma over the square root of N. We want to find little n. So what we have to do is rearrange this and solve for little n. Okay, so to do that, we can basically go square root of n is equal to Z alpha over 2 times sigma divided by capital E. And then we can say n is equal to Z alpha over 2 times sigma divided by capital E squared. Any questions? Okay, so what is the Z-score for a 90% confidence interval? Does anyone remember? I will give you a hint. It is one of the only 3-digit Z-scores. Nice, good job. Okay, so we have n is equal to 1.645 times 42 divided by 12 squared. So that should give us 33.1488. So therefore, we need 34 observations. Okay. So whenever we run a sample, yeah, there's 4, okay. Okay, so, sorry, okay, 1.645 is 3 decimal places. So sorry, the hint was it's the Z-score with 3 decimal places attached. Okay, so then we get n equals 33.149. And whenever we do a sample size calculation, we round up. So even though this would round to 33, whenever we are using this formula to compute sample size, we always round up, because otherwise we might actually miss the target because we won't have quite enough information. Okay, so always round up when finding little n. Any questions? In part B, it says, if researchers perform an upper-tailed hypothesis test about mu, what is the p-value if the test statistic is z equals 2.37? All right, so we have upper-tailed test for mu. Okay. So that means that if we were to write out the general form of our hypotheses, we would have mu is equal to some value versus the alternative that mu is greater than some value. We are told in the question that the test statistic is z equals 2.37. And what we are being asked to find is the p-value for this test. Okay, so we would start off by sketching our z curve. Then we would mark down where our test statistic is located. And then we can highlight the region of the p-value. So we're conducting an upper tail test. So the p-value is going to be the area above the test statistic. So in this case, the p-value is equal to the probability that Z exceeds 2.37. So what we need now is our Z table. So we open up our Z table, which is here. Okay. All right, so if we go into our Z table and we're looking for 2.37, here's 2.3. We scroll over to 0.07. So that means that 2.37 is right here. Okay, so this quantity here, 0.9911, that is going to be the area underneath the curve below or to the left of our test statistic. Okay, so we want the area to the right. This is going to be 1 minus the area to the left. So that's going to be 1 minus 0.9911, which is 0.089. Any questions? Yeah, I subtracted it from 1 because the value that's given in the normal table is the area to the left of the test statistic. So the value in the table would be the area, the size of this white unshaded part here. I want the green shaded area here. Everything underneath the curve must be equal to 1. So in order to get the part that I want, I need to subtract the area to the left from 1. Right, yeah, so technically, so the probability that Z is greater than 2.37 is equivalent to the probability that Z is less than negative 2.37. So if you were to look up negative 2.37 and take that value, you would get the right answer. But technically, in this problem, the p-value is greater than Z greater than 2.37. So you have to you would get the right answer, but you need to indicate that you're trying to find this area by using the other value. Does that make sense? Okay. But that approach is perfectly fine. If anything, that's easier than what I did. Yep. Well, I mean, like we can actually we can play a little I wish I had more room so I can be cheeky. Okay, so we'll play To reject or not reject? Okay, so the rule is, and never changes, you reject when the p-value is less than or equal to alpha. Okay, so at alpha 0.1, would we reject or not reject? Yeah. Okay, what about alpha 0.05? What about alpha 0.01? Ooh, controversy. So again, the rule is if less than or equal to, you can reject. 0.0089 would round to 0.01. That would be equal to, so you can still reject. So you do not reject when it's strictly bigger than. You can reject when it's less than or equal to. Does that make sense? Exactly. P-value strictly greater than alpha, do not reject. So here, we do not. Okay, any questions? Well, technically speaking, like if you round the p-value to 2 decimal places, this would go 0.09, which would then go 0.01. Any other questions? But the nice thing is that in terms of rejection, it doesn't matter. Okay, problem 3. An observational study was conducted to determine whether or not 3 different scoliosis treatments were successful in preventing the spines of 286 females from curving beyond 6 degrees. Okay, so we have a contingency table for the treatments and the whether or not the treatment was successful in preventing the spine from bending beyond 6 degrees. So we have brace, stimulation, observation, and then we have whether the treatment was successful or whether it was not successful. Our data are summarized in a two-way contingency table. Okay, so for the final, so when you see a two-way table, think chi-square independence test. Right? So the two-way table is almost like a giveaway as to the type of problem you're going to be asked. The only hypothesis test that we have studied that uses data in a two-way table is the chi-square independence test. So if you see data laid out like this, you should automatically start thinking, okay, I'm going to have to do a chi-square independence test here. Now, with that being said, you can see part A says, suppose a chi-square independence test was performed and a test statistic of 28.128 was calculated, right? So again, it's just kind of a little bit of a hint to help us clarify what unit we're working in. Okay, so part A, part I. I don't know why this is so separated, but whatever. Okay. Compute the expected number of results that did not fail given a brace was used. So we want expected number of successes for the brace. Okay. So for a chi-square test, the expected values are found by multiplying row total by column total over the sample size. So this is going to be the row total for the brace multiplied by the column total for successes divided by the sample size. So that's 111 multiplied by 189 divided by 286, which is equal to 73.353. What were the null and alternative hypotheses for this test? Okay, so it's a chi-square independence test. The null hypothesis will always be that the variables are independent or not associated. And the alternative will always be that the variables are not independent or are associated. So we're going to have, in the simplest expression, treatment and result are independent versus the alternative, treatment and results are not independent. Okay, part 3 says, or asks rather, what is the critical value for this test? Okay, so we have alpha equals 0.05. We want to find the critical value for the test. So imagine that we're on step 4. So I'll just say step 2 here. Okay. So we have a chi-square test. So we can sketch out our chi-square curve. Our critical value is going to be a chi-square on 0.05. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So we have 3 rows and we have 2 columns, right? 1, 2, 3, 1, 2. So 3 rows, 2 columns. So we have 3 minus 1 times 2 minus 1, which is 2 times 1, which is 2. So this is a chi-square, or the critical value is chi-square 0.05 and 2 degrees of freedom. All right, so we go back. We open up our chi-square table. We're going to match 0.05 with 2. That gives us a critical value of 5.991. Okay, and then part 4 says, what is the conclusion of this test? All right, well, if we were to complete the hypothesis test, our test statistic was 28.128. So are we going to reject or not reject the null in this case? So we're going to reject H0. If we wanted to, we could see that this is true because our test statistic is way into that rejection region. Okay, so then what we actually want here is the conclusion. So we have at the 5% significance level, the data provide sufficient evidence to suggest that the treatment and results are not independent. All right. Any questions? All right. So last one. According to the 2016 census, the distribution of the Canadian population can be represented by the following relative frequency distribution. Okay, so Annalise, that long formula for the DF only applies when you're doing a 2-sample independent test. So that's the first thing. That's only in one situation. On the final exam, you can do the minimum of N1 minus 1 versus N2 minus 1. So on the final, you don't need to use that formula. But it's only in the case that you're doing an independent 2-sample test. Okay, so we have here a relative frequency distribution. So similar to before, when we see this, we should be thinking chi-square goodness of fit. So if we see a relative frequency distribution on the final, automatically we should be thinking this is probably a chi-square goodness of fit test, because this is the only data that lends itself to that type of test. All right. Okay, part A says, if one Canadian is selected at random from the entire population, what is the probability that they are from Northern Canada? Okay, so the probability that you are from Northern Canada is going to be 1 minus 0.066 minus 0.615 minus 0.315, which I think is 0.003. .004. Okay. I'm just going to try and finish this. Suppose that a random sample of 21,394 Canadians are selected from the entire population, and a chi-square goodness of fit test returned x squared equals 10.313. What is the p-value associated with this test? Okay, so what's going to happen here is we are trying to find the p-value for this chi-square test. Okay, so here's our chi-square curve. Here is our test statistic. We want this green shaded part here. So we need the probability that the chi-square exceeds 10.313. All right, now for this problem, the degrees of freedom is going to be the number of objects or the number of cells minus 1. So we have 4 different outcomes in this test. So our DF is going to be 4 minus 1, which is 3. All right, so we go to our chi-square table. We have 3 degrees of freedom. 10.313 is going to fit right here. So we're going to be between 9.348 and 11.345. So our p-value is going to be between 0.025 and 0.01. So we can say, since 0.01 is less than the probability of interest is less than .025, then 0.01 is less than the p-value is less than 0.025. All right. Part 2, do the data provide sufficient evidence that the distribution of the Canadian population differs from what is stated in the 2016 census at the 1% significance level? Explain. Okay, so in part 2, we can say, since the p-value is greater than 0.01, then the p-value is greater than alpha. Therefore, we will not reject H0. Now, since we're running a chi-square fitness of fit test, age 0 would be the Canadian population follows the distribution stated in the 2016 census. So we have no evidence that the population differs from that given in 2016. Okay, sorry, I'm just going to finish it up and then I'll take questions. The last part, how many of the 21,394 randomly selected Canadians would you expect to be from Western Canada? Okay, so in part 3, we want the expected value of the West. This is going to be n multiplied by the probability that you're from the West. So this is 21,396 multiplied by 0.315. Oh, 21,394. Multiplied by 0.315, which is 6,739.11. All right. Oh, yes. Thanks, Daniela. Okay, sweet. So I'll hang around if anyone has any questions. I'll just wrap up by saying good luck with all your finals. I hope that the semester went smoothly. I feel like a broken record saying like I hope we're back in person soon, but this is just the way that things still seem to be. And I have office hours today. I'll have office hours next week as well. I'll post the times of those later in the week. And if anyone has any questions, I'll hang around for a bit. And otherwise, I will maybe talk to you again. And if not, good luck on your finals and have a nice Christmas and New Year's.